Welcome to the video channel of the CRC 768 Managing Cycles in Innovation Processes. In this video, we will present you the integrative sub-project Action Goal-Oriented Interactive Visualization of Model Dependencies to reduce complexity in the cycle-oriented transdisciplinary design of PSS innovation processes. In today's innovation processes of product service systems, so-called PSS, we have an increasing complexity. The complexity results, on the one hand, on the transdisciplinary environment of the stakeholders with varying areas of expertise who work together within the innovation process. On the other hand, the complexity is based on the multitude of different models with different levels of abstraction in the various disciplines, their dependencies, and the information flows between them. The result is a complex heterogeneous model landscape with dependencies between the different models, as well as a variety of views of the stakeholders about the process. Such interdisciplinary projects within the innovation process require a common understanding between the stakeholders. However, difficulties in communication and comprehension often results from different underlying individual mental models between the stakeholders. Based on the individual mental models of the stakeholders, a shared knowledge base about the cycle management in innovation processes can be derived. In order to solve these problems, we will offer an interactive cross-discipline visualization approach to reduce the complexity by visualizing model dependencies under consideration of the context and the individual task of the stakeholder within the innovation process. Such visualization can improve the communication between the disciplines in the transdisciplinary environment and assist in the assessment of impacts and changes in the innovation process. The challenges of this sub-project of the CRC 768 firstly is the elicitation of teams' mental model through interviews and workshops to find dependencies and interconnections between the different models used within the different disciplines. Secondly, in the implementation of an integrative, interactive visualization approach to visualize these dependencies, and thirdly, the evaluation by means of use cases for an application example. Let's take a closer look at the 4 use cases which are meant to represent and bring a solution to 4 different problems that real companies may face during their operation. These are change management, which means changes in a PSS, for example regarding product life cycles, technology life cycles, or manufacturing structure cycles. Inconsistency management, to identify and resolve inconsistencies within cross-heterogeneous models and to encourage cross-discipline collaborative innovation. Knowledge management, for the acquisition of new knowledge and maintaining old knowledge. And custom integration in processes of the evaluation of innovation concepts and prototypes. For each of the use cases, we are creating a map of model interconnections based on the interviews and workshops, which is representing the team's mental model. This map is being applied for solving a representative problem for a battery change for the so-called cycle demonstrator, which is represented by a rental bicycle. As you can see in the created map for the mental model of the use case inconsistency management, many sub-projects with many different models are involved. If we zoom into the map, we will be able to see all detailed interconnections between models and their elements. Here you can see a choice of models. Blue arrows show the different outputs of the model elements which are presented in the information box. The red arrow in turn represents the input of the model and establish an element-level connection between 2 models. Moreover, elements such as information flows were identified and represent possible valuable information that is passed from one to another model, but at the same time it is not a strictly necessary element for the model's operation in comparison to the inputs mentioned before. This means that the model would still be able to operate without the information flow, but some processes can be sped up or improved due to its implication. What does this mean for our interactive visualization? Particularly, industry models can contain thousands of entities. Hence, mechanisms to enhance comprehensibility are mandatory. Consequently, some sort of information filtering, aggregation, and/or abstraction is required for the visualization approach. For various problems from the information visualization domain, so-called overview and detail paradigm is used. Following that, a top-level view is created that contains all the models that are included in the production and innovation process. Each node in the top-level view is representing one model instance. If there is at least one link between an entity from one model instance and another entity from another model instance, an edge in the top-level view is included between the corresponding nodes. For the detailed view, one or more model instances and, with that, their graph representations are chosen from the top-level view and visualized in the detailed view. The nodes of each chosen models are now visualized in this view, and with that, all the interconnections between these models. The nodes of each model instance are layouted inside a respective cluster, which get layouted on cluster level, similar to the top-level graph. For our example of inconsistency management, that means initially we have an overview of our whole model landscape. If there is an inconsistency between two models, the nodes that are representing the corresponding models and/or the edge between these models are marked. Now we can click on the edge or on the two models, and in a second view we see both models with their elements and all links between the two models. After that we can filter so that only the correspondent nodes and edges are visualized, which are involved into the handling of the inconsistency. Here you can see the interactive three-dimensional visualization of the top-level view. In the top-level view, there are various filter options. For example, all models of a particular type can be selected, such as descriptive models, simulation models, or technology models, and so on. We can also search for single models, and furthermore, we can select the different use cases so that, in the second view, we see only the models which are included in the chosen use case. If we click on a node, we are able to get additionally information about the chosen model.